this problem, we're going to take a look at what happens with Part 2, some books call it Part 1 of the fundamental theorem of calculus. In this problem, I've got the derivative with respect to x of an integral that goes from the constant value to a function of x of a function of t. Now, in order to analyze this, we're going to take a look just at the antiderivative first. When we find the antiderivative of that, the t becomes t squared over 2, and sine t becomes a negative cosine t. And then we want to evaluate that from t equals 1 to t equals cosine x. And we'll just use our the other part of the fundamental theorem of calculus to find that. So if we plug cosine x in for t first, then t squared over 2 becomes cosine squared x over 2, and the minus cosine t becomes minus cosine of cosine x. When we plug in the 1, the t squared over 2 becomes 1 squared over 2, and the minus cosine t becomes minus cosine of 1. Now don't forget, we're taking the derivative of this whole thing. So if we take a look at that whole back portion, that 1 squared over 2 minus cosine 1, that's just going to be a constant value. There are no variables in there at all. So when we take the derivative, that part becomes 0. Now the front part is a little trickier. That cosine x squared, we're going to have to apply a chain rule, and I didn't go too far into the steps of this, but what happens is that 2 from the cosine squared comes to the front, and then it cancels with the 2 in the denominator. So all that's left is cosine x. But then we apply the chain rule and take the derivative of the cosine x, and that's where that negative sine x is coming from. So that's cosine x times a negative sine x. On the back part, we do a chain rule again, so we start with the outside portion, the negative cosine, and the derivative of that becomes negative sine, and we leave the inside part alone. And then we have to multiply that by the derivative of cosine, which is negative sine x. If you have trouble with any of this stuff, just pause it and go back through it slow, because that's a lot in one step. Now what I'm going to notice is that in both my terms, I have a negative sine x, and I want to get it out of there. I'm going to add those green parentheses just so we can keep track of what was there originally and what's left after we remove the negative sine x. So if I take the negative sine x to the outside, in that first part, I'm left with only a cosine x. In the second part, after I remove that negative sine x, I still have 2 negative signs there. So I've got negative sine of cosine x, which becomes positive sine of cosine x. And then I'm just going to write it one more time so we can see it looking a little more clean without the green parentheses. Now this is the connection I want you to see. If we compare the original question with the result we have so far, you can see that the t has become cosine x, and the sine t has become sine cosine x. So what we've done is replace the t with cosine x in both parts of our solution, and that's where our rule is going to come in. If we look at what we have left here, my negative sine x is the derivative of cosine x. Then inside the parentheses, the cosine x is just cosine x plugged in for t, and then the sine cosine x is cosine x plugged in for the t in that portion. So if we wanted to write a rule for that, basically what we're saying is that if I take the derivative with respect to x of some antiderivative that goes from a constant as the lower limit of integration to a function of x as the upper limit of integration of a function of t, then my result is going to be the derivative of f of x, or the derivative of the upper limit of integration, times the function that we started with, that g of t, but with f of x plugged in now, so g of f of x.